of periodic operators left off by Peter yesterday. I'm going to continue to talk about those. Peter has done a lot of work for me already, so I don't have to. I will just have to refer to his lectures. But I will have to make certain things a bit more precise, and I intend to, because this is about a concrete method in the theory of periodic operators, I intend to be a tiny bit more technical than Peter. So I'm going to talk about the periodic operators. So we can begin by thinking of the following standard operators. This is one of the examples considered by Peter. So this is the Schrödinger operator. This is the Laplace, as usual. This is a real valued function. Let's assume that this is a very nice one, and it is a periodic function. And we are looking at those on L2RD. What is important here is that dimension is arbitrary. So we will concentrate mostly, later we will concentrate on multidimensional case mostly. The second important example that I will discuss in detail is this. This is the magnetic Schrödinger operator. Again, here we have the function v, the same as before. This one is the vector valued function, d components, and all of them are real valued. And physical meaning, of course, of this vector field is the magnetic vector potential. And let me just write this down, magnetic. Okay, so what about this mysterious gauge transform method? Most of you, if not all, know what gauge transform is. What I called gauge transform will be a generalization, certain generalization of that transform. And in more precise terms, what I'm going to do, I'm going to construct for each of those operators, and for more general ones, I'm going to construct a transform which will diagonalize, loosely speaking. Diagonalize the operator. Or more precisely, I will replace those operators with some other operators with constant coefficients. And we know that if you have constant coefficients, you already essentially know the spectrum. You can compute it immediately. But this is, I repeat, very loosely speaking. It is not that straightforward.
And you have given the hypothesis on V or A? Not yet.
Not yet.
Is real values, I presume.
Yeah.
And I said that.
Yeah.
Everything is real valued unless otherwise stated. Right? So that the operators are self-adjoint. I will also assume that all the functions, all the coefficients, they are infinitely differentiable. I don't want to go into all these details, how to relax conditions on potentials and so on. Let's just concentrate on the essence. So first I need to introduce some notation even before I start talking about these methods. So here it is. So periodic potentials, therefore I have a lattice. Lattice I will denote by gamma. So this is lattice in RD, full rank. So there are d linearly independent vectors in the lattice. Then I have dual lattice, which will be denoted by, like this, gamma dagger. This is the dual lattice. It will be convenient for me to assume that they live in the same space. Peter emphasized that he wants you to see those two things in two different spaces. For me, it doesn't really matter. I just identify those two spaces with one another. Now, fundamental domain, again, let me just quickly remind you. So for this lattice, fundamental domain will be denoted by O. This is the calligraphic O. It is very easy to do in tech, but when I started writing it on the paper, I realized that it's not so easy, but I have to stick to this notation. O is fundamental domain. And for the second lattice, for gamma dagger, it will be, so that is the fundamental domain. What is fundamental domain? So if you take this domain and shift it by vectors of the lattice, you will tile the entire space without overlaps. So that's the definition. There are many choices of fundamental domains. I will not worry too much about this multitude, and I will just choose some standard domains. For example, if gamma is 2 pi z cubic lattice with h 2 pi, then the fundamental domain will be just a cube, one side open, one side closed. Sorry, 2 pi here, like that, with h 2 pi, right? So if you shift it by vectors of length 2 pi along the axis, coordinate axis, you tile the whole space. And this is precise, right? Because this is exactly how I choose the construction of this cube. Now, now, dual lattice will be just the integer lattice, and the fundamental domain is therefore the unit cube. Another notation is the torus. This is very convenient to have a torus as well. It is the quotient of the space, of the entire Euclidean space. So that's the torus, the notation. As a rule, it will be sufficient for us to assume that gamma is a cubic lattice. But at some point, I will want to talk about more general lattices, so I prefer to keep the general notation. And sometimes it is faster to write just gamma instead of ZD. So this doesn't really matter. And another thing I forgot to mention, so this is called the lattice determinant. So this is a positive number associated to the lattice, and this is the volume of the fundamental domain. The interesting fact, elementary but remarkable, is that this lattice determinant doesn't depend on the choice of the fundamental domain. So whatever you take, for example, if you take all these Brillouin zones, there are plenty of those, the first one, the second, the third, and infinitely many. All of them have the same volume, of course, because they all tile the space if shifted by vectors of the lattice. So this is the lattice determinant. Okay, so this is basic notation. Now, some simple things. So once we are dealing with periodic things, right, we expect some functions on the torus TD here. I want to introduce some notation related to that. So first of all, Fourier transform, this is the standard notation. This is what I will use for Fourier transform. F, calligraphic F, this is Fourier transform. And I will write it down, although everybody knows what it is, because I want to specify this normalizing factor. Sometimes people define Fourier transform without this factor or with D. I want this. I want this transform to be unitary. Okay, so this is a unitary transform for all good functions. Now, the next thing I want to define Fourier coefficients of a periodic function, right? So if we have a function on the cube, L2 function on the cube, or smooth function on the torus, here are the coefficients. Here I divide by the this is lattice determinant here, normalizing factor, and then the standard notation here. Okay, so theta will be a vector from the dual lattice. Okay, and this is all, well, I can define this, of course, for all L2 functions. Well, it's standard facts, but I just need the notation.
For completeness, you can write integral over RD, right, for Fourier transform.
Thank you. Right, so this is the usual arrangement. If no limits of integration are provided, the integral is supposed to be over the entire Euclidean space. But, you know, I count on the audience to set it right. Yeah. Okay. Now, now I have to make a little jump here. Not literally, of course. So we started with those operators. They are familiar objects, differential operators with variable coefficients, of course. But one of the messages of this method is that you have to learn how to work with pseudo-differential operators. And I'm saying that not because I want to be fancy and I want to generalize things as much as I can, but because the method I'm going to talk about is intrinsically pseudo-differential. So we have to talk about those as well. Okay? So I will talk about pseudo-differential operators with periodic symbols, and I will leave this blackboard for those definitions. So we have a function. So this is a complex valued function in general of two variables. Both of them are in RD, so this is x, and the dual variable momentum xi. I assume that this function is periodic. Function b is periodic in x, excuse me. Okay, so shifts do not change the value. And now I can define a pseudo-differential operator with this symbol by the following formula. So the notation for this thing will be OP of B, so operator with symbol B, and what it means is the following. So how does it act on the function u? You take the function u, you take Fourier transform, okay, then you multiply by the symbol, okay, you multiply by the symbol. So far nothing serious happened, I just multiplied, and then you take Fourier transform back, and that's all. Okay, I didn't leave enough room here, but there is also this normalizing factor, 2 pi to power d over 2, this is the standard one, and then you take Fourier transform, as I said, and that is going to be x xi g psi. Okay? All right. So this is the pseudo-differential operator. I do not assume that the audience is familiar with pseudo-differential operators. And shall I assume that? Okay. And my message is that you know there is a huge theory of that. I don't know how many papers or books written about pseudo-differential operators. And when I started working with those, I realized that whatever I want, I can do it with my bare hands. I don't need to look anywhere. See? If you want to learn advanced things, that you open the books. But we are going to do everything now here on the board. This is easy, in fact. Once you got used to that definition, everything, you know, goes without problems. So let me show you an example. Do I need? Before I show you the example, I want to say the following. So we like self-adjoint operators, or at least symmetric. So how do we make this symmetric? it doesn't look very symmetric, right? You take Fourier transform, you multiply by something which is already asymmetric. So there is x, which is the variable here, and there is no variable y, which is here in the Fourier transform. However, one can make it symmetric by looking at the Fourier coefficients, the ones that I defined over there. You see the second line? By looking at those coefficients of these symbols with respect to this variable. So this is the function depending on two variables. I take Fourier coefficients in this variable. So, and this is the notation here. Okay? This is Fourier coefficient of the symbol in variable x on the torus or on the fundamental domain. And then if I impose this condition, then you can just do it by direct calculation to check that the operator is going to be symmetric. So I'm going to say that this is a symmetric symbol. Okay? Let me check. Yeah, that's correct. Well, that's easy to understand, right? If you have just a function in some simple cases. If you have a function of x, right? If your symbol is just a multiplication by a function, then operator of b will be just multiplication by a function. And if v is real valued, then definitely this condition is satisfied because the Fourier coefficients satisfy this relation, right, for real valued function. So it is a natural generalization. Okay, now another thing, if your operator is just minus delta, it is also pseudo-differential operator where b is just psi squared. Very elementary things, but I feel better if I tell them to you, right? So that you don't have to. And this is obviously also self-adjoint, or more precisely symmetric operator. Okay, very good. Now we can see that this operator makes sense for these examples: multiplication by a function, smooth periodic function, and this kind of thing. But because we are going to use them systematically, we need to extend the class of symbols and to make to understand when this integral makes sense. And we have to do actually even more, because as I said, we're going to work with those systematically. I have to build a calculus of those operators. I have to understand how to multiply them. I have to understand how the commutators behave and all this sort of stuff. And we're going to do it. This is not going to take too much time, because I'm going to introduce the classes, natural classes, in this setting, in the periodic setting. So what I will do, let's write down classes of pseudo-differential operators. So pseudo-differential operators, they use letter psi here, the capital one. I've been told if I use p, this would mean partial differential operators. So this is pseudo-differential operators. Now I'm going to look at the Fourier coefficients, and I will see how they behave. First thing, the growth or decay of Fourier coefficients I will measure with the weight function. Right, so this is a real valued function greater than or equal to 1. or just separated from 0 would be enough. And I also assume that it doesn't grow too fast. So there is a I will write this and then I will explain. Right, so if you move if you move xi by vector eta, then you have this bound with the universal constant and some positive number kappa here. So you, for example, you can say that these weights cannot grow faster than polynomially, for example. And by the way, there will be lots of constants around, universal constants, and I don't want to label them all starting from today, 1, 2, 3, 145, and so on. What I will do instead, I will write, instead of this inequality, I will write the same with the double inequality sign. This will mean that there is a constant. This means exactly that. Okay?
What do you mean by angular bracket?
Good question, thank you. And this is, yeah, well, I will, this is what it is. This is just eta squared, but you add 1 to separate it from 0. There is a terminology for that. There is a term for this. This is called Japanese norm. Japanese because I think the first person who used that was some Japanese mathematician, and it stuck. So, right, okay. Now, what kind of classes do I have in mind? So what I will assume is that if I differentiate, this is the gradient, I take power s of the gradient, right? So it's going to be lots of coordinates. It will be a tensor. I differentiate it with respect to xi, and I assume that this quantity for every s, it is all infinitely differentiable, for every s, it's going to satisfy the following bound. First of all, I have this weight function here. So the weight, I will have some power alpha here, so there's a general common growth for all derivatives of w to power alpha, and then every derivative kills one order of growth. Okay? Then I have right, and then I need to assume how they decay in parameter theta, and this will be that. So I will assume that they decay faster than any power of the parameter theta.
Is S a Mach index?
No, S is this is the gradient, so I can take powers. So it is S is 0, 1, 2, and so on. And L actually as well. Of course, the constant that will be here will depend on S and on L. Okay? So the best constant will be denoted by, I will need a notation for it. So let me define it. I've been training actually to do this before the lecture. Yeah.
So much for the training.
Yeah, breaking the mic.
So that's your assumption of the symbol.
Yeah, these are my assumptions on this. I'm going to break this all together. So assuming that good. Right, so this is kind of norm. Actually, it is not kind of norm, this is a norm, right? So alpha here, and then this is the supremum of, we know what to do here, so here we have to multiply it by theta psi, w minus alpha plus s. Here we are. Right, as I said, this depends on L and S, of course. So if I were to conduct some tedious calculations with those quantities, I would have to remember to put here two indices, two subscripts L and S, but for us it will not be important. The main parameter that we have to keep track of is the parameter alpha, the growth. Okay? So what I will write usually is this. So which means that I'm looking at this for some values of L and S, or for arbitrary values of L and S, depending on the context. It will not be very important for us. I would like to make a remark about this. Yes?
Why do you want in your estimate that indication theta, since theta ranges over gamma?
Yeah.
No, it's okay. It's okay. I got it. Sorry, mistake.
All right. I need to make a quick comment about this weight function W. If you look in the monographs on pseudo-differential operators, then you will see that there can be quite general weights there. I would like to use general weights, not because, again, I'm kind of apologizing all the time, but it will stop. I'm using general weights not because I want to be very general, but because natural choice of the weights in what we are going to do will be very diverse. For example, so examples. One of the important types of the weight will be this. So this is psi, that Japanese norm that I defined before, to power beta, and beta is between 0 and 1. So look what is happening if we're looking at this formula. So every time you differentiate with respect to psi, you lose some growth in psi, but this growth will not be integer. It will not be just integer power that you lose. You lose a fractional power. These things happen, and that will be very important for me if I ever get to that point, to have this kind of weight. Another choice of the weight is this. I will not explain the meaning of these constants here, but the psi is there, so that's already enough. So rho and omega are positive constants, some constants. And here you see you have the weight, which measures the distance from psi to the sphere of radius rho, right? So if you go away from the sphere, the weight grows. And this constant here is to prevent this weight from vanishing on the sphere. Okay, so that's another choice. And yet another choice, very simple one, another constant. Just a constant weight, right? But this constant can be chosen large depending on spectral parameter or anything you want. But this is also a legitimate choice in what we are going to do. Okay? So for as long as possible, I want to keep W general, and then I will specify which of those I will have to choose. Yeah.
And the second example, isn't it the same as the first with beta equal to 1? Isn't it equivalent to that?
It is equivalent if you are willing to let the constants depend on the parameters. It's true, but the parameters will be changing as well. I didn't say what the meaning of this parameter is. This is going to be spectral parameter essentially, and it will grow. So the equivalence is not exactly useful here.
That's what you are saying. This is a sub-generalization of this Hermander classes, right? SM rho delta, right?
I don't think it is generalization. It is essentially the same thing, maybe in a slightly different setting.
Allowing for various weights, right? Which are not necessarily this Japanese thing.
Yes, true. True. So this is the standard class, the standard Hermander class that you can find in essentially any book on the differential operators. Well, I think I'm ready now to introduce the main object after half an hour of study. So now I'm going to define the operator that I'm going to study. So it's going to be a free operator. So let me write it like that. It's going to be a pseudo differential operator with symbol H, right? H sits well with this capital H. So H x psi is H naught psi. The unperturbed part, a natural one, will not depend on x. It will be constant coefficient operator plus b x psi. So what is H naught? H naught is psi to m with a positive number m. In other words, so I put here 2m and not just m because I want H naught to be Laplace to power m. Okay? So we're talking about polyharmonic operator. But m can be just arbitrary positive. It doesn't have to be greater than 1. It can be very small as well. And the perturbation here is from the class. Oh. All right?
Made mistake, sorry, excuse me.
Okay. Right, okay. Let me just go back one blackboard. So if these quantities are finite, we say that B is in the class S alpha W. Okay? I said everything except for the introduction of this class. So in this class. So beta is in the class S alpha, and the weight will be one of those that I chose there, psi beta. Okay. Now, if you're familiar with operator theory, that we'd better ensure that this operator is well defined. So we want to take this symbol in such a way that it grows slower than the symbol of the unperturbed operator. So here I will take alpha beta greater than, strictly less than 2n. Okay? And this quantity is natural to be called the order of the perturbation. It is not exactly precise, but we will refer to that as the order. Okay? So a bit later, we will see that indeed this perturbation is infinitesimally small with respect to operator H naught, so it is defined on the same domain. Okay? So the domain of the operator of this operator will be, because of this, it will be the space H to M RD. Okay? And as I said about this infinitesimal boundedness, this is going to be the main Actually, that was the first statement, and this is the second. This is because of the infinitesimal boundedness. Right. Now, what I want to do now, I want to describe the Fourier transform of the operator. Now here, it will be very easy for everybody because I'm just referring to Peter's lectures with small variations. Okay. So what we want to do, we want to identify the space. So I will denote this by curly calligraphic H. This is this Hilbert space we are working on. I will identify this space with the direct integral. Okay, I can write straight away. This is the L2 space on the fundamental domain dk, and the integral is taken over the dual fundamental domain. When I write this equality, I actually mean the not equality but unitary equivalence, so to say, right? So what is the unitary equivalence? It is the Fourier transform that we have already seen before. So here it is, Fourier. And I remember there was a discussion how to call this, Fourier, Gelfand, or something else. I would like to add another name. Yes, Bloch transform. So it is Fourier, Bloch, Gelfand transform. But we will be using only Fourier, just for Bloch.
You have to add Zach and many others.
Don't stop. Faites vos jeux. Brilliant, thank you. I will stop now, okay, if you don't mind. So, Bloch, Gelfand, Zach, we will just drop it. But remembering that quite a few people, came up with a similar construction. I never read what Bloch has written. But I just believe the books.
Seems like you only do one dk or ds, right?
Yes.
Fourier definitely didn't write this transform.
So probably we should throw Fourier out.
Oh, it's safer.
Okay, I will denote this by this again by calligraphic U, by curly U, and then I'm sorry, I will use the small letter U. I hope I will not confuse them. So this is a function which depends on two variables, x and k. X will be in the fundamental domain of the lattice, and k will be in the fundamental domain of the dual lattice. Okay, this is how we do that. Now here I have, now I need to remember exactly what is happening. Here I have the lattice determinant of the dual lattice. Okay, this is important to remember. And then I have minus ikx exponential, and then the sum. And now you will see the familiar sum, that's what Peter wrote before, and it will be ik, wait a minute, how come I don't remember it? No, that's right, ik but with minus ik gamma, and then here we are. Okay, so how do we get this? This is what I repeat what Peter defined before, but let me just talk a little bit about it for you to get used to it. So you take a function in L2, or it's better to take smooth, fast decaying functions. For example, functions from the Schwartz class, right? Infinitely differentiable functions decaying faster than any polynomials with all their derivatives. Right, so we take this vector, this x, in the fundamental domain, and then we take all the shifts along the lattice, and because it is fundamental domain, we're going to probe every point in every shift of the fundamental domain. Then we collect them together, okay, and that is the transform. It is almost the same as Peter's, except that I have this factor here. If you remember, there were no factor of that type in the transform defined by Peter. Why do I need this factor? Because you remember when you take this function now, you started with a smooth function here, take this function now, and now go around the torus. When you go around the torus, in Peter's version, you get a phase factor when you come to the initial point. You remember that. For this function, you get no factor, because this factor will kill the phase factor, so you are dealing with periodic functions.
So Peter's function is k quasi-periodic, and your function, you make it back periodic, right? By canceling this quasi-periodicity due to that factor.
I couldn't have said better. Yeah, exactly. So this is periodic by canceling that phase factor. Useful. Okay. Another thing I wanted to emphasize, again, is that this is just a little note, a very useful note as well, that if you take the Fourier transform now, so we're talking about periodic functions now, right? So we take Fourier transform in the variable x, and then this Fourier transform is obtained from just Fourier transform of the function u, the one defined there, at the point theta plus k. So theta is in the dual lattice, and k is in the dual fundamental domain.
You probably mean Fourier coefficient on the left.
Sorry?
On the left, probably it's not Fourier transform, it's Fourier coefficient.
Fourier coefficient, I'm sorry, yes. On the left it is Fourier coefficient defined over there, and on the right this is Fourier transform. So it's very nice. I like that interpretation because it makes things a bit clearer, because look at this function on the right first. You take, let's take one dimension, right? So you take one-dimensional lattice, and then instead of studying this Fourier transform, this is the graph of the Fourier transform of the function, you slice it up and you study it in every strip. Okay? So this function, theta will be the number of the strip, and k will be the variable inside the strip. So you just slice it up, collect it together, and now you have your new representation. Okay, so that's useful fact to remember. Nice. What about the operator? Now that's an important thing. The operator that I defined over there, what happens to that operator? We already know from the general theory that this operator will be represented again as a direct integral. Okay, so when we take functions of that type, the action of this operator will be just multiplication for fixed k. It will be multiplication by an operator valued function. This is because everything is periodic. This is because it is periodic. The operator will not mix up different k's. It will not be an integral operator in k. It will be multiplication operator in k. Let me write this down. So H is, more precisely, it is not equality, but unitary equivalence. It is going to be, let me see, u minus 1u. This is unitary equivalence. It is the direct integral dk hk. All right. Now, what is hk? And this is something that will be, again, important for us. Now we're going to have pseudo-differential operators on the torus. Here we have them on the space, on the entire Euclidean space. Now we're going to have operators on the torus. And here they are. Now this is the sum. I theta x. Then we have h x. Oh, yes, okay. Theta plus k. And then I have the Fourier coefficient of the function u. Now the factor, normalizing factor, is again the volume lattice determinant here. K is in the dual domain, right? So we have that type of thing, right? So now, by writing this formula, I have defined, in fact, the pseudo-differential operator on the torus. If you have a function u, I should say that I'm looking at infinitely differentiable functions for the sake of simplicity at that moment. So all these things are well defined, they decay fast. And look how it acts. It acts in exactly the same way. You multiply by the symbol. The symbol depends now on the discrete variable. And then you collect all the, you reconstruct the function, taking the inverse Fourier transform, so to say. This is how it happens, okay? What did I want to say? Right, examples. So for those standard operators that I want to study, for standard operators, so h naught of k will be operator. No, I shouldn't do that. It will be an operator of that type with the symbol. Let me write it like that. The symbol will be theta plus k to n. Right? This is what it is. And for h of k, it will be theta plus k to m plus bx theta plus k. For the Schrödinger operator, minus delta plus v, if we take the slice, if we take the fiber labeled k, we're going to get theta plus k squared plus v of x. This is the symbol. And for the magnetic operator, well, a very similar thing. Let me write this down for further reference. I will need this. This will be, I need to look it up. Yeah? I don't even remember what it is. Let me write this down. So this is going to be theta plus k. This is the first guy which is the same as Laplacian, minus 2a of x theta plus k plus I gradient a. This is gradient with the dot, okay? So this is divergence of a plus a squared plus v. Okay, so that's the symbol. Is the symbol symmetric? Well, we know that this operator is symmetric. right? So it should be, this symbol should be symmetric, and it is. If you look, if you check this property, it will be satisfied, okay? Although it doesn't look that way, it will be satisfied. Okay. Now, the nice thing about those operators on the torus is that they have discrete spectrum. This is the whole idea, that if you want to study the spectrum of a periodic operator in the entire space, it doesn't have discrete spectrum. As we know, it has, very often it just has an absolutely continuous spectrum, right? How to study that spectrum? Reduce it to the discrete one using the slices. So we sliced it up. And now we have operators with discrete spectrum. The eigenvalues will be denoted by first I'd better say about the domain. Self-adjoint. The operator h of k that I defined is self-adjoint on h2m on torus. Okay, that was important that we have that factor removed, the phase factor, that now we're dealing with periodic functions. So the domain is the same for all operators h of k. It is just h2m, okay? For all k. Convenient. And then eigenvalues, we denote them in the standard way, right? These are eigenvalues of h of k. They are labeled in ascending order. That is important. And of course we count multiplicity. So eigenvalues can coincide, but they will be still counted as two different ones. Okay. Now, when we study eigenvalues, we use the counting function. So the counting function n, lambda h of k, right? For a number lambda, I count all eigenvalues below lambda. So this is the number of those j's below lambda. Okay, good. What else I need to remind? Right, now how do we build spectral bands? We take those functions. Now we look at those eigenvalues at functions of k. These are band functions. Let's write this down. Band functions. Or they're called sometimes Bloch functions as well, but never Fourier functions, I guess. So the spectral bands, and this is letter sigma. Sigma j. Spectral band label j is just the set of values of the jth band function. So this is the set of values of jth band function over all k in the dual domain. Okay? And the spectrum is built out of bands, so the notation for the spectrum is this. Okay, take all of them. Well, I'm getting very close to the point, but I'm also getting close to the end of the lecture. So I wanted to tell one thing at the end here. So we're going to study the band gap structure of the spectrum. In particular, one of the questions that I'm going to address will be whether we have finitely many gaps or infinitely many gaps. Okay? So it will be important to understand how those functions behave. Right? So if you remember what Peter said. If we are in the multidimensional case, that these functions can have overlapping ranges. In one-dimensional case, it is impossible, but in multidimensional, so if we think of this interval as the dual fundamental domain, then what we can have is something like that. So we have function like this, and then another one like that. So this is lambda 1, this is lambda 2, and of course their ranges overlap, okay? So we want to understand that. But let's ask a simpler question. What will happen if we have an unperturbed operator? If we forget about all these funny things here, and we will look only at, I have already erased that. If we look at H naught, what can we say about bands for this operator? You might ask, who is going to study bands for the unperturbed operator? We know everything in advance. But if we intend to study perturbations, we need to understand what is the band structure for this guy as well. And for this guy, eigenvalues are easily found. You remember I had this formula here on one of those boards that this is the symbol. This is the symbol of the operator, right, on the torus. Well, if it is the symbol, then you can now read off the eigenvalues. So these are the eigenvalues of this operator. They're explicitly found. Nice. And of course, we can count those eigenvalues as well. And if you count them, H naught k, what you will find, looking at this formula, that the number of eigenvalues below lambda is nothing but the number, I will write it like that, this is the sharp sign, the number of lattice points, which I denote by n, or actually theta would be just fine, number of lattice points inside the ball of radius rho, and rho here is related to the spectral parameter like that. Okay. So the counting function for those eigenvalues, for the free eigenvalues, for the unperturbed operator, coincides with the counting function for the lattice, for the dual lattice. Okay? Because of that formula, these are eigenvalues. So this is the ball with center minus at the point minus k, right? So if you start moving k, this ball is moving around. So some eigenvalues will, some lattice points will leave the ball, some will come in. So this is how the counting function changes. And studying this function, it is a very non-trivial problem, right? This is the number theoretic problem, which is very serious one. So how come that we know eigenvalues explicitly and yet we can't say much about them? And the answer is very simple, because they are labeled in the wrong way. They are labeled by lattice points, and we want them to be labeled in increasing order by integers. And when you start relabeling them, you get in trouble because of this counting thing. So this is why the study of this function, counting function, is a big pain. There are many results, but they are not complete yet. There are many results to that effect. Some of the results for periodic operators depend. If we want to explore this connection with number theoretic problems, then I will show you some results which are linked to number theoretic properties of the lattice. And you will see how they change when we remove any assumptions about the nature of the lattice. But it will not happen today. It will happen next week. Thank you very much.
Yeah. Any questions?
While I understand the very good reason why we order the eigenvalues by increasing order, would there be other orderings of the eigenvalues that would yield some information about the spectrum relating to problems like this?
Would it be what? Sorry?
Could we choose a better ordering of eigenvalues so that that could yield information in a better way?
Well, you see, the question is, why do we order them in increasing order? After all, maybe it's better to order them. For example, sometimes it is more natural to order them according to their analytic properties. Sometimes you have analytic branches of eigenvalues. But then you turn the perturbation on, and everything breaks down. The only thing that doesn't break down is ordering in the increasing order. So this is very unstable. An arbitrary ordering is unstable. You can lose everything just like that in a second.
Other questions?
I get trying to see a bigger picture that from what, as little as I know, from pseudo-differential calculus, right, which is built on like Fourier transform, and the like differential operator becomes multiplication by the symbol, right? Instead of naively. Is it? Are you saying that you could, in the sense, you could construct similar calculus with respect to all these guys, Flock, Blockade, and so on, transform rather than Fourier transform, bearing in mind covering all kind of operators with periodic coefficients, but not only differential operators with some kind of
Not only
pseudo-differential operators with the periodic coefficients, right?
Yes,
Ultimately, right?
Yes, correct. That will be the calculus that covers these operators, yes.
Other comments? Doesn't seem to be the case. So
Thank you.
again.